Hi everyone, I'm Yifan from the Computer Science Department at University of Illinois at Urbana-Champaign. Robotic manipulation of deformable objects in the real world has a variety of applications, such as packing deformable objects, robotic palpation in biomedical settings, etc. One of the challenges involved is building deformable object models from noisy, real-world data. Compared to humans, robots are quite bad at doing this. If a human touches a piece of chicken leg for a few times, this person can take this experience and guess quite well how it feels to touch a piece of steak. At the same time, doctors can diagnose a variety of diseases just by palpating and feeling the anomalies. In this paper, we will take preliminary steps toward equipping robots with similar capabilities, where deformable objects are modeled from a small number of interactions, and the robot can then predict the outcome of contacting arbitrary rigid objects. Here is an overview of our method. Shown on the top left, we use a robotic system to collect the visual and tactile data from a small number of pokes. Then we build a point interaction model of this deformable object. The model is then used in a semi-empirical simulator that solves for deformation and contact range with an arbitrary rigid object. In the bottom right animation here, the color of the deformed object represents the amount of surface deformation. Notice that we can continue learning by simply retraining the point model with new data. Our method is a semi-empirical approach that integrates machine learning with physics. The general idea is to combine well-understood physics with learning that abstracts away physics that are not well understood or are difficult to compute or tune the parameters involved. Common modeling approaches such as the finite element method require an object's geometry and its material properties to be represented by a volumetric mesh model. Mesh models are challenging to build from noisy sensor data, and calibrating its material properties is also hard. On the other hand, pure data-driven models would need a large amount of training data, which is oftentimes too prohibitive for robotics tasks. Our method takes advantage of both by using a simple analytic model plus learning with a small number of features. The semi-empirical simulator is inspired by the classic Kersian contact theory, which is explained by the graph on the right. It says that when a point on an object surface is deformed, an area on the surface deforms with it, and the deformation at 2 points can be related by the equation shown here. The constant c controls the shape of the deformed surface. An important observation is that the deformation at a surface point is a combination of external force and the effects of the neighboring points. This inspires our approach in that the contact range between a rigid and a deformable object can be looked at as summing up forces from individual points. Throughout the project, we assume that the object is elastic, quasi-static, and that the interaction forces are dominated by normal deformation rather than friction and shear deformation. The constant c is picked by observation. However, for future work, we could determine this constant using camera tracking the shape of deformation during poking. Here, we first define two terms. The nominal displacement is the displacement of a surface point from the original deformable object surface, and the actual displacement is the amount of displacement caused by external force. The displacements are always non-negative. The nominal displacement at a point is always no smaller than its actual displacement plus the contribution from neighboring points. If this becomes an inequality, this means that this point is no longer touching a rigid object, and the actual displacement has to be 0. This relation between nominal and actual displacement is that of LCP. Looking at the equation here, R is the distance between the surface points, and each entry of the matrix is a shape function. The matrix vector product sums up the contributions of all the actual displacements. We solve the LCP by iteratively assuming equalities, solving the system of linear equations by matrix inversion, and removing the points with negative actual displacements. The initial guess of the nominal displacement will be calculated by a collision detector, and the points are shown as blue dots in the picture. This concludes the modeling part of the algorithm, and the results are the nominal and actual displacement of individual points. Then, if we train a point model that gives forces from displacement, we can compute the contact range at this contact. Next, we talked about how we collect data for point models. We use the robotic system shown in the picture. It is a UL5E arm equipped with an RGBD sensor and an N-factor 4-stroke sensor with a tapered probe. The object is fixed to a flat table to prevent gross movement during poking. In the future, we could potentially track gross movement of the object with a camera. The picture on the right shows the 5 testing objects used in this project, where each object has varying stiffness across the object surface. A point cloud model of the object is first acquired by RGBD sensor. Notice that the visual model acquired is usually noisy and slightly biased. In some cases, the object could even have fuzzy, poorly defined boundaries. The robot arm then pokes at a few random points on the object visual model in a normal direction while recording force in the normal direction. An example of the force displacement curve from one poke is shown. Note that the force is greater than 0 when displacement is 0, which shows the bias in the acquired visual model. Here, we try to learn the force response when poking at a point on the deformable object. The goal of user learning here is to overcome the noisy and biased visual model and the heterogeneous testing objects, where directly modeling these would be extremely difficult. The model input is the position of the point being poked on the object original surface and the poking depth in the normal direction. The output is the force magnitude. We use AutoML to perform this task. We're able to learn a reasonable model under 30 seconds with data from 10 pokes. The animation here represents a force prediction across the lamp object at depths 0.5 mm using model learned from different pokes of data. As the number of pokes increase, the models becomes increasingly more refined. One can see the varying stiffness across the object. The model also captures the bias in camera data in that at 0 depth or even negative depth, there is force felt, although it is not shown here. Here we show some qualitative results. The sloth object is being poked at by a rigid object shown on the bottom left. It is the line probe. The color shows the deformation across the object while the object is being poked. Examples from the other testing objects. We can see the grooves on the lamp and the bird that would fit the probe geometry at deep penetration. The shoe and the vest objects are stiffer, so the constant C in the shape function are much greater. As a result, the grooves are harder to see. To evaluate the performance of our approach, we also collected validation data using the line probes in a similar manner to the point probes. We also trained models to predict the total force and torque on this probe using data from 10 random pokes. Overall, our simulator performs slightly worse than pure learning. It is better on the lamp and bird object and slightly worse on the vest and shoe object. We believe this is mainly due to the fact that the vest and shoe are made of composite materials. As a result, the shape functions approximate the deformation of these objects suboptimally and lead to errors in the simulator. The key advantage of our method is that it is essentially zero shot, and we do not need to reacquire new training data with novel rigid objects. And we can also predict for force responses for different roles and pitches of rigid objects, which are currently not included in the learning-only training set. Finally, we show a demonstration on a simple packing problem as an illustration. Given a rigid box with a piece of lamp already packed into it, we would like to know if we can pack another rigid sphere into it. In particular, we would like to know at what positions can we put the rigid sphere into the box such that the interaction force with the lamp does not increase 2 newtons. We basically do a grid search, and the plot of minimal possible height of the sphere on the XY grid is shown here. Solving the LCP and occurring the point models take about 12 milliseconds on average. For future work, we would like to relax the assumption that interaction forces are dominated by normal deformation. At the same time, one related to the topic of meta learning, things we already have a database of objects. Can we learn new object models faster and with less data? We would also like to handle contact between deformable objects rather than just rigid and deformable objects. Finally, we would like to apply our method to more challenging planning problems. Thanks for watching.